Welcome, everyone! Today, I am thrilled to present microgpt-zig, an exploration into atomic AI training. This project represents a first principles deconstruction of the GPT architecture, implemented entirely in pure Zig. By focusing on zero dependencies and a codebase of just 700 lines, we aim to strip away the abstraction layers typical of modern machine learning. What remains is the pure logic of the transformer, providing a clear, transparent window into how these powerful models actually function. Let's explore how this minimal approach can deepen our understanding of artificial intelligence.
Modern AI development relies on massive abstractions that often obscure the atomic operations of the hardware. As shown on the left, a typical stack involves multiple layers, from PyTorch and Python down to CUDA, drivers, and C++ libraries. While these provide significant utility, they create a weight of abstraction that masks how the machine actually functions. This slide explores the deconstruction of that stack, moving toward a leaner implementation like microgpt-zig. The central question we are posing is, what happens when you strip away these frameworks and library layers? Our assumption analysis targets the belief that building a GPT necessitates a dedicated deep learning framework. This is a critical assumption with a high impact. If it is proven false, it means millions of lines of library code are effectively optional for understanding core mechanics, opening the door to much more direct and transparent AI implementations. The architecture of this project is defined by its radical simplicity. Everything lives within a single file, src/main.zig. By deliberately avoiding external frameworks and libraries, the implementation relies exclusively on the Zig programming language. This single source file encapsulates the entire pipeline, including the tokenizer, the value structure, the state dict, the core GPT function, and the backward pass for gradient computation. This streamlined approach results in a highly compact codebase of only 730 lines. Despite its minimalism, the system achieves a wall time of 4.94 seconds on an Apple Silicon CPU, establishing a high-performance baseline that is both transparent and easy to audit. Let's examine the first assumption often made in systems programming, the idea that the OS knows best. Traditionally, when we need memory, we rely on the operating system's general-purpose allocators. As illustrated by the tangled red path, this process is inherently inefficient for high-performance needs. Each request triggers a sequence of complex events, from page allocation to mmap and munmap system calls, which introduce significant latency. This stems from an unstated assumption that standard tools are sufficient for high-frequency training loops. With a criticality rating of 8 out of 10, the consequence is clear. Standard allocators frequently invoke costly syscalls. In microgpt-zig, we eliminate these syscalls entirely during the training step by using a fixed buffer allocator and a simple pointer bump strategy, represented by the direct green arrow. By managing memory ourselves within a pre-allocated block, we avoid kernel-level overhead. This optimization, marked as enhancement number 3, resulted in a substantial performance gain, reducing execution time from 1.53 seconds down to 1.38 seconds. Let's move to our second assumption, the belief that data structures are computationally cheap. Frequently, developers rely on the O of 1 theoretical complexity of hash maps, assuming this translates into negligible real-world overhead. However, in our specific case, tracking visited sets in a backward search, the reality was quite different. Our original implementation utilized an auto hash map, which necessitated continuous hashing and complex collision handling logic. This overhead, particularly when hashing pointers, accumulates massively at scale. To optimize this, we eliminated the hash map in favor of a simple 32-bit unsigned integer counter embedded within each node. This value is checked against a global step counter, replacing heavy hashing logic with a straightforward integer comparison. This fundamental shift from complex data structure management to basic arithmetic resulted in a substantial performance gain, bringing our execution time down from 4.94 seconds to just 1.52 seconds. Assumption 3 explores the misconception that math is just math in the context of computational graphs. In many standard implementations, an operation like division, denoted here as div of a, b, is treated inefficiently by breaking it down into two separate operations, a power node for b raised to the negative first power, followed by a multiplication node. This approach doubles the necessary infrastructure for a single logical operation. The fix is straightforward. By using direct implementations for negation and division, we can effectively halve the graph node count. This highlights a common unstated assumption that the cost of creating a computational graph node is negligible compared to the mathematical operation it performs. However, when we scale, this overhead becomes significant. The ultimate consequence of reducing these nodes is a marked decrease in memory pressure, which otherwise compounds across the entire model vocabulary.
Assumption 4 challenges the notion that automatic growth is always optimal. In a typical dynamic resizing scenario, arrays expand as needed, which seems convenient. However, when using an arena allocator, this leads to substantial waste. Because arena allocators do not free individual buffers until the entire arena is cleared, every incremental resize leaves behind an abandoned block of memory. In our specific case, this resulted in thousands of useless buffers per training run. To understand the scale of the issue, our topo and stack lists were starting from 0 and doubling roughly 16 times per step. We had been operating under the unstated assumption that this resizing process was efficient enough to ignore. By shifting to an explicit capacity management strategy, using ensure total capacity to pre-allocate 40,000 slots up front, we streamlined memory usage and significantly improved performance. This single optimization, marked as enhancement number 5, reduced our runtime from 1.37 seconds to 1.08 seconds, proving that managing growth explicitly can yield major efficiency gains. The speed of simplicity is clearly demonstrated in this comparison of execution times. Starting with a baseline of 4.94 seconds, we implemented a series of optimizations focused on architectural hygiene. The removal of the hash map provided the most significant initial reduction, bringing the time down to approximately 1.5 seconds. We further refined performance using fixed buffers and pre-sized lists, ultimately reaching a final runtime of just 1.08 seconds. This represents a total 4.5x speedup achieved entirely through streamlined code architecture, without the need for specialized hardware like a GPU or any third-party libraries. The slide before you illustrates the significant overhead often inherent in high-level machine learning frameworks. On the left, we see the standard PyTorch setup, represented by a heavy weight. While PyTorch provides immense flexibility and ease of use, it comes with a massive footprint of dependencies and substantial memory requirements. On the other side of the scale, we have microgpt-zig, a minimalist implementation written in the Zig programming language. Its efficiency is striking. It utilizes a mere 16.3 megabytes of memory, retires 47 billion instructions, and operates with 0 external dependencies. This comparison highlights a common but unstated assumption in our field, that meaningful model training necessitates a high-end GPU. However, the reality is that CPU optimization remains a highly viable path when the underlying hardware is properly respected. By stripping away layers of abstraction and writing code that is sympathetic to the processor's architecture, we can achieve high performance and training capabilities even on standard hardware. This project serves as a proof of concept that efficiency doesn't always require more hardware. Sometimes it just requires better software. Turning to our future assumptions, we operate on the premise that memory layout remains static. This leads us to several pending optimizations. First, we plan to implement a pool allocator designed to pre-allocate contiguous slabs of value nodes. As you can see in the diagram, this transitions our system from a state of fragmented memory to a much more structured and efficient layout. Next is the manual reordering of struct fields. Specifically, we aim to pack critical fields like grad, children, and end children so they reside within a single 64-byte cache line. An important part of our assumption analysis reveals a common unstated assumption, that compilers automatically optimize struct field layout for cache line efficiency. In reality, this is often not the case. The consequence is that manual field reordering becomes a requirement. By doing so, we can prevent performance-degrading cache misses along the hot path of our backward pass, ensuring optimum throughput as shown by the aligned cache line mapping here. The assumption that serial processing is inevitable often stems from the inherent difficulties of backward traversal. When we iterate through a topological list in reverse, we are essentially performing a pointer chase, which results in poor spatial locality. To mitigate this, we use the @prefetch optimization, which is designed to allow the CPU to overlap memory fetches with gradient computation to hide L2 and L3 latency.
The efficacy of this approach relies on the unstated assumption that a CPU can successfully predict memory access patterns during a reverse topological linked list traversal. As shown in the illustration, while we aim for the predictive foresight of the green runner, the reality is often closer to the reactive stance of the red runner. In practice, complex pointer logic confuses hardware prefetchers, preventing them from effectively anticipating the next required data point. The micro philosophy is centered on finding the most atomic way to train and run inference for a GPT. By stripping away the layers of abstraction found in traditional frameworks, we can achieve a level of optimization that is otherwise impossible. Understanding these fundamental atomics allows us to control the very essence of the model's execution, where every additional layer is viewed simply through the lens of efficiency. This approach, implemented here in Zig, draws direct inspiration from Andrej Karpathy's original microgpt.py, focusing on clarity, performance, and a deep understanding of the underlying mechanics of artificial intelligence.